Hello, everybody. So it's time to start the 3D UI session. So in this session, we have excellent 5 papers. So 3 conference papers and 2 invited TBCG journal papers. Each paper, they have 7 minutes. So after all the 5 presentations, we have a single long Q&A session. Okay, so let's start. The first talk is bullet comment for 360 video, and which is going to be presented by Yi-Jun Lee of State K Laboratory of Virtual Reality Technology and Systems, Beihang University, China. So please start.
Okay, can you hear me?
Yeah, I can hear you. I can see.
How about my slides?
Yes, please start.
Okay, I'm going to start. Hello, everyone. I'm Yi-Jun Lee from Beihang University. It's a great honor to give the presentation here. Today, I'll introduce our paper, bullet comments for 360 video. Bullet comments, also known as the Manku in Japanese and Damu in Mandarin, are technology that enables audiences to post the live time-anchored comments over the playing video to share their emotions and thoughts with other audiences. They have been an appealing feature offered by social media platforms like YouTube and Bilibili to strengthen audiences' social connection and help them better understand the video content. However, this technology cannot be directly applied to immersive 360 videos due to the specialty of VR environment. For example, the headset audiences can freely navigate their viewports and perform controller-based interactions. Some related work is about 360 video collaborative viewing. The left one proposed the Colo VR system to support multiple users reviewing and communicating in their VR headsets, but it requires all users to attend simultaneously for online communication, and their method is hard to deal with large real-time data. The right one constructed virtual classmates by synthesizing previous learners' time-anchored comments, which can help learners have the sense of being accompanied and achieve better learning outcomes. But it is for viewing traditional videos in VR headsets. Therefore, in this paper, we developed 2 user studies to explore how to display and insert bullet comments in immersive 360 videos. During the experiments, users will sit in a swivel chair and experiencing 360 videos while head-mounted display and controller. In the first study, we want to figure out what is the most popular approach to display bullet comments on 360 videos. We believe that the display of the comments needs to be time-space anchored, which means in addition to aligning with the commenting time, a live comment should be visualized spatially consistent with the corresponding visual content. Therefore, we developed 4 display methods based on this criteria. In planar horizontal, bullet comments are displayed on a virtual planar canvas attached to the whole field of view of the user. Once the user's field of view covers the position of a time-space anchored comment, the comment enters the user's field of view from the right boundary and slides evenly and horizontally to the left boundary within a 20-second period. Catering to common reading habits, it simulates the movement of bullet comments used by current video streaming websites. In spherical static, each time-space anchored comment appears at its insertion position on the spherical surface formed by 360 video, starting from the insertion timestamp, similar to planar horizontal. The comment disappears after a 20-second period. Fade in and fade out effects are used on the text for smooth transitions. In spherical horizontal, each comment appears at its insertion time and a position on the sphere. Moreover, the comment horizontally and counterclockwise flies along the latitude from the insertion position for 20 seconds with a 6 degree per second angular velocity. In spherical vertical, each comment appears at its insertion time and position on the sphere and flies upward along the longitude from the insertion position with a 6 degree per second angular velocity for 20 seconds or till reaching the pool region. According to the experimental results of engagement, social interaction, and preference from 20 participants, spherical horizontal and spherical vertical are the most and the second most popular display methods. In the second study, we want to figure out which bullet comment insertion method will audiences find more natural and easier to use. We hope that the operations for comment posting should be as easy as possible so that the user can perform fast and accurate interaction with no need to pause the video. Therefore, we developed 2 insertion methods based on this criteria. In select and drag, the user activates the interface where the candidate comments are circularly distributed by clicking the trackpad. Then selects a comment by touching the corresponding trackpad region. After selection, the user drags the comment to the target position on the video by holding the trackpad and inserts the comment by releasing the trackpad. In locate and select, the user first points at the target position, target insertion position on the viewport using recasting, then clicks the trackpad to activate the comment insertion interface. After that, the user selects a comment by clicking the corresponding trackpad region. Then the selected comment is immediately inserted at the target position. We further combined them with spherical, horizontal, and spherical vertical display methods to form a 2x2 condition combination. In this video, rows represent different display methods while columns represent different insertion methods. Results from 16 participants revealed there is no interaction effect between display and insertion methods, while select and drag was more preferred by participants. Our work also has limitations. First, we only propose several representative display and insertion methods for bullet comment on 360 videos. Designs related to other attributes, for example, color, size, and transparency are also worth studying. In addition, we assume that bullet comments bring users a better experience. A comparison to no comment method could be conducted in the future. Also, bullet comments have different spatial linkages with the video content. Whether they affect the user's preferences in display methods can be further studied. That's all. Thanks for watching.
Thank you very much. Okay, so let's move on to the next talk. And while he's preparing, I forgot to tell you, but please make many questions on the dedicated channel on Discord. Okay, and actually all the presenters are also encouraged to make questions to other presenters. All right, the second talk is an evaluation of virtual reality maintenance training for industry hydraulic machines. So, and then which is going to be presented by Hoang of School of Information Technology, Yiqin University, Australia. So please start.
Thank you, Kiyoshi. Hello, everyone. My name is Hoang from Yiqin, as Kiyoshi mentioned. Today, we'd like to talk about our work with Stefan, Greuter, and Simeon Taylor, looking at the virtual reality for industrial maintenance training. So we conducted a comparative evaluation of a training method for maintenance of a hydraulic power unit, the HPU. This is partnered with an industrial manufacturers in Australia. This unit is quite large. It's about 5 to 2 by 3 meters because our client is actually building this for their mining industry partner, where they actually use the whole machine to flip the whole train carriage of iron ore over. So we were given a digital twin versions, virtual model of the machines, and we actually do model simplification using Houdini because our target platforms are Quest 1 and 2. They have very limited processing power. So the training interface we have is actually built around a QR code, like a virtual QR code. The idea is that later on we can actually move that to AR system if we need to, so we can actually have physical QR code on the system. So the virtual checklist interface, our main training, because we actually focus on very structured maintenance tasks where there's like tasks that they have to complete one by one for sort of different types of sort of maintenance, mostly maintenance actually. And as you can see on the checklist, people can actually go through the checklist. There's a checkbox on the right-hand side, you saw a little bit earlier, and they actually tick that to complete the task. There's a little videos window that actually shows what they need to do. These videos are created within the VR environment. So actually the virtual, the video instructions of the task inside VR. And then the user will have a set of tools that actually can interact within VR, so exactly focus on more experiential kinesthetic learning environment to provide the realistic interactions. So then we conducted a user study with 2 separate cohorts. One will be in university students where we can recruit, and the other are professional contractors where our industry partner recruit. So it's slightly different methods of study between the 2. So we do a between subject study for our students, because we can actually allow to create, we can recruit multiple. So end up having 23 participants, our students, 12 for VR, 11 for traditional training methods. For our industry, we have to do within subject. We can only recruit about 12 industry participants. So most of the tasks, these are the training. So we actually conduct the VR and traditional training on site. The training is part of the training program for our industry partner. So they actually had a very structured program to do that. And so the participant, this is a summary of all the measures. You can exactly find more details in the papers as well. So for the student cohort, we had a lot more time. So we focus on their learning style questionnaire. We have the training experience, satisfactions and self-confidence in learning, educational practice questionnaire. And for those who have the VR on, we ask them to complete NASA and presence and embodiments as well. And for our industry cohort, we actually had quite limited time, so we only do a little bit of training experience questionnaire. But both cohort, at the end of their training, they actually managed to have an authentic assessment on the physical hydraulic machines within on-site on the factory floor, scored by a separate trainer in terms of their performance, their confidence, cleanliness, and safe work practices. So the result shows that our student participant experience a bit more satisfactions and higher self-confidence in learning while training with VR compared to traditional techniques. But we did not find any significance in the industry result at all, which is quite interesting. And that's the thing that the main contribution of our paper is sort of reflecting on 2 different cohorts. So this is the video of the actual assessment training within the hydraulic machines, because we're quite lucky that our industry partner is actually building one of those for shipment, and before they manage to ship out to their clients in a different state in Australia, we have access to those for a couple of days to actually do training. So based on the, we also had an interview with all the sessions after, all the participants afterwards. So those are the training in the VR. So based on the interview, showed that the student cohort appreciated scale, size, positioning of the machines. They actually had the muscles memory from training, but our industry partner cohort don't usually have the muscle training. They appreciate that for industry participants, they appreciate that the VR training is easy to use with authentic experience. Physics simulations, we didn't do physics because, like you said, like all the things are floating in mid-air because we didn't have like a tool belt or a virtual tool belt or anything like that. Our student participants didn't have any problem with that, but our industry participants are sort of had a lot of problem with that because that's not what they are used to in their day-to-day. So they sort of bring that up a lot as well. One interesting comment from a group of industry participants is that because they have actual experience of going on site and services those machines, they comment in that the VR model is perfectly shiny and beautiful, but on site, when they're actually like working on maintenance on actual machines, they don't look like that because there has been sort of wear and tear, sort of different kind of elements, everything faded, etc. And that's actually what we find very interesting in terms of sort of VR training. Yes, everything is perfect, but then when we work on an actual system, there's sort of wear and tear in the physical environment that we can't simulate. So these are sort of the different summaries here. You can just read more on the paper, and that's concluded the end of my talk. Thank you, everyone.
All right, thank you very much. Okay, so let's move on to the third talk, which is GazeDock, gaze-only menu selection in virtual reality using auto-triggering peripheral menu, and which is going to be presented by Yi of Zihan University. Please start.
Okay, thank you, Kiyoshi. Hi, everyone. I am Yi from the Institute for Network Sciences and Cyberspace of Tsinghua University. Here, I'm very happy to present GazeDock, a novel gaze-only menu selection technique in virtual reality using auto-triggering peripheral menu. Yeah, with the rapid increasing of the popularity of virtual reality and augmented reality, a number of commercial products have become common in our daily lives. However, menu selection as a basic interaction task was usually achieved using the hand controller or mid-ear hand input, which limited the input precision and would introduce fatigue during usage. In recent years, gaze input for VR and AR has attracted increasing attention as it provides natural and potentially high-performance interaction. There have been a number of commercial products that incorporated gaze tracking, including Pupil Labs, Tobii, and HTC Vive Pro Eye. To facilitate the gaze-based menu selection experience, researchers have proposed various input techniques, including dynamically changing the appearance of the menu, using hierarchical menu, using gaze gestures, and pursuing. However, given the trade-off between efficiency and robustness to false triggering, few techniques have explored the ability of false triggering prevention for gaze-only input. To this end, in this work, we aim to design and implement a fast and robust gaze-only menu selection technique in VR. We first carried out a user study to examine the participants' natural gaze behavior in VR. We recruited 12 participants from the campus with an average of 2.2 years of experience with virtual reality. We used the HTC Vive Pro Eye headset as the experiment apparatus, which provided the gaze tracking data for analysis. Moreover, we tested 4 typical kinds of VR applications: Island Journey, a first-person shooting game; Job, a work simulation application; Rec Room, a multiplayer online platform; and Blocks, a 3D design tool. We analyzed the general gaze distribution across all participants. Results show that gaze points gathered near the center of the participant's field of view and distributed in a slightly flat elliptical range. In comparison, existing works have found that the range of intentional gaze movement could reach 44 degrees in left, right, and down directions, and 28 degrees in up direction, which was greater than our results. This suggested that leveraging the gap between the intentional and unintentional movement range of gaze was possible for interaction. Further, individual difference of angular range could be greater than 50%, which highlighted the necessity of personalization. Design GazeDock, a ring-shaped docking menu around FOV. Users trigger the menu by moving the gaze towards the edge of FOV into the menu. And then they selected a target item by moving the gaze out from the item. GazeDock is auto-triggering by the gaze and becomes hidden when the gaze leaves. Now, according to the results above, we designed a personalization process for GazeDock, including identifying the vertical and horizontal movement range of the user's gaze, and then calculate the ellipse parameters. We finally multiply the height and width of the ellipse by 0.9 for ease of use. When designing the menu triggering and selection confirmation mechanism of GazeDock, we observed that intentionally approaching GazeDock is typically consisted of two phases. The gaze angle increased rapidly in phase 1 and keep for a while in phase 2. This feature in phase 2 was different from that during natural gaze movement. Therefore, we designed the algorithm with two connected time windows with size of 100 milliseconds. Phase 1 detects the initial gaze angle was below a threshold of 10 degrees, and the final gaze angle reached the inner boundary of GazeDock. Phase 2 detects that the gaze angle keeps above the angle. Simulation results on the data from study 1 show that this algorithm could effectively reach a false triggering rate of 0.26 times per minute. To model the participants' gaze point ability on GazeDock, we conduct another user study with precise selection tasks and different item densities, respectively. For the precise selection task, the participants were asked to move the gaze from the center to the indicator and keep for 500 milliseconds. We found that the angular arrow followed well with a univariate Gaussian distribution, and polar arrow showed tendencies in different directions, whereas absolute polar arrow was not observably different in different directions. Also, we tested the participants' pointing performance with 5 levels of item densities. For each density, we arranged the letters as the item label in alphabetic order with a random start position, and participants were asked to select the target item as quickly and as accurately as possible. Results show that significant effect of density was found on error rate, selection time, and throughput, and the optimal number of items was between 4 and 8. Finally, we evaluated the usability of GazeDock in real tasks. The task was to explore the 3 scenes: laboratory, magic house, and bedroom. Find the props that do not belong to the current room and move them back to their target positions. Accordingly, there are 6 supported interactions: move to the laboratory, move to magic house, move to bedroom, pick, drop, and exit. We tested 3 techniques, including GazeDock, dwelling, and pursuit menus. The parameters of all these techniques was fine-tuned in pilot study. Results show that the average selection time of GazeDock was 471 milliseconds, faster than the time of dwelling and pursuit. Also, the false positive rate and false negative rate of the 3 techniques was compatible, with no significant difference found among them. Finally, subjective ratings indicated that GazeDock was significantly more preferred by the participants in terms of efficiency, learnability, effortless presentation, and overall preference. Please look at our paper for more details. Thank you for listening.
All right, thank you very much. So let's move on to the 4th paper in this session. The 4th one is OctoPocus in VR, using a dynamic guide for 3D mid-air gestures in virtual reality, and which is going to be presented by Katherine Fennedy of Information System Technology and Design Pillar, Singapore University of Technology and Design. So please start.
Hi everyone, can you guys see my screen? Yes, okay. So my name is Katherine, and in this presentation, we will demonstrate how our adaptation of the OctoPocus guide to VR is not only feasible, but also beneficial. In VR, buttons and menus are still predominantly used today due to user familiarity with pointing and clicking. However, they occupy space and do not facilitate expert performance. Gestures, on the other hand, can be performed in the 3D space around the user and increase the input vocabulary. But because they are not self-revealing, users need to explicitly discover, learn, and memorize them. One solution is to use a guide. A guide can be static, like crib sheet or cheat sheet, that displays what can be done and what the result will be. Or a guide can be dynamic, like OctoPocus, which filters feed-forward options based on a partially performed gesture. OctoPocus also provides a continuous feedback by dynamically rendering the line thickness of each path, such that less likely paths get thinner and eventually disappear while the most likely ones remain. The relevant literature would be that by Delamere et al. They use a Kinect for 3 degrees of freedom indirect input, a mouse button for delimiting gesture, and a 2D desktop monitor to render 3D guides. Their primary investigation is on how feedback and feed-forward visualizations affect speed and accuracy of 3D movement. In comparison to our work, we focus on the VR context, which is fundamentally different in terms of rendering and input. Delamere et al. Also based their comparison against a video crib sheet in a 4-person preliminary study. But it remains unclear if a video crib sheet is any better than the static one tested by Bo and McKay. Thus, we chose to implement a VR-adapted crib sheet for the baseline in our study. In addition, we measured not only speed and accuracy, but also learning, recall, and usage rates. Despite all these differences, we adopted one of their key contributions to reduce visual complexity. In other words, our work focuses on replicating Bo and McKay's evaluation of both static and dynamic guides for the VR context. In our implementation of OctoPocus, pressing the trigger button and pausing for a moment reveals a rendering of all gesture paths. As the user starts moving in a direction, gestures that are less likely fade away. Eventually, this filters out all gestures except the desired one, and they finish drawing the gesture by releasing the trigger. Pressing the grip button enters an exploration mode where they can rotate and translate the entire guide to gain a better perspective to the 3D gesture space. This exploration mode can be activated at any time while viewing the standard guide. For crib sheet, pressing the grip button reveals a static 3D rendering of each individual gesture arrayed in a grid. This can also be rotated and translated. Once the desired gesture is located, the sheet is dismissed by releasing the grip button, and the gesture is drawn using the trigger button. Both OctoPocus and crib sheet were tested using gesture training and testing tasks. Each task trial begins by touching a start sphere. Then a target gesture label appears and they draw the gesture. The trial ends when they see the label of the recognized gesture. The task is the same for both training and test. The main difference is that during test, no guide is available. While during training, guide is available, but it is not compulsory to use the guide. But if they choose to do so, the trial is marked as novice, otherwise it is marked as expert. Overall, we follow Bo and McKay's general procedure, where only 8 out of the 16 available gestures were trained and tested. The test follows immediately after each training, and together, this forms one block. We had a total of 3 blocks to form the main phase, and the main phase is sandwiched between a pre-test and a post-test. During pre-test, each of the 16 gestures were presented in a different order and with no guide provided, so participants were instructed to provide their best guess. This is to measure baseline recall. This is to measure baseline recall performance without any prior knowledge. So all 16 gestures were also tested in the post-test. The main difference is that half of them had been practiced in the main phase and the other half had not. So this is to measure incidental learning. We analyzed our time measures for novice trials. So overall, OctoPocus performs better in terms of input time, but worse in terms of reaction time. For accuracy, OctoPocus is more accurate than crib sheet for all 3 measures. In terms of learning, both guides help participants to recall more gestures after each training block at B1, B2, and B3, and also similar performance in terms of gestures they were not explicitly trained on. Both Bo and McKay's and our results show that OctoPocus is more accurate than CryptSheet. However, differences lie in terms of reaction and input time. So this could be due to the extra dimension of 3D gestures that make it harder to execute and learn as compared to the 2D gestures. Although our design is very different from Delamere et al. Study, we can still make meaningful comparisons. So in terms of trial duration, our guides are faster by 36 percentage point, while our gesture recognition is more accurate by 20 percentage point. So this suggests reliability in our algorithm implemented. For more detailed descriptions and discussions, please refer to our full paper. Thank you.
Thank you very much. All right. Okay, so let's move on to the final talk in this session, which was written by the Zimin Hu et al. Of the School of Computer Science, Peking University, China. But actually, the instead of live presentation, we will play the pre-recorded video. So can you start, Stefan?
Hello, I am Jimmy Hu from Peking University. My paper is EHTask, recognizing user tasks from eye and head movements in immersive virtual reality. Let's start with the background of this work. Understanding human visual attention in VR is crucial for many important applications, including gaze conditional rendering, redirected working, layout optimization, VR content design, gaze guidance, as well as LOD management. Well, however, previous works on visual attention analysis typically only explored one specific VR task and paid less attention to the differences between different tasks. Moreover, existing task recognition methods typically focused on 2D viewing conditions and only explored the effectiveness of human eye movements. Specifically, previous works have explored visual attention analysis for free viewing tasks in VR, visual attention analysis for visual search tasks in VR, task recognition for 2D images, as well as task recognition for 2D videos. Compared with prior works on visual attention analysis, we explore 4 different VR tasks using the same settings. We also analyze the differences between different VR tasks. Compared with previous works on task recognition, we focus on immersive VR instead of 2D images and or videos. We explore the effectiveness of both human eye movements and head movements rather than only human eye movements. Task recognition methods have many important applications in the area of virtual reality. They can be applied to adaptive virtual environment design, low-friction predictive interfaces, as well as attention-aware intelligent systems. Well, our contributions are listed below. First, we provide a new dataset that contains human eye and head movements and 4 task conditions. Furthermore, we analyze the patterns of human eye and head movements and review significant differences across different tasks. Finally, we present EHTask, a novel learning-based method to recognize user tasks in immersive virtual reality. We utilize the 360-degree VR videos as our stimuli. We ask participants to finish 4 tasks when viewing the videos. The tasks are free viewing, video search, silence, and track. We collected the task categories, users' eye movements, and their head movements for further analysis. This table shows the statistical characteristics of human eye movements in the 4 tasks. For each item, the differences in the fonts of 2 tasks indicates that there exists a significant difference between them. We review significant differences in terms of mean fixation duration, fixation number per second, mean saccade duration, saccade number per second, mean saccade amplitude, as well as fixation distribution dispersion. We also analyzed the autocorrelations of human eye movements in the 4 tasks. We review significant differences in vertical direction. We also analyzed human head movements. We review significant differences in the aspects of mean absolute horizontal velocity, mean absolute vertical velocity, mean absolute horizontal acceleration, mean absolute vertical acceleration, as well as velocity distribution dispersion. We further analyzed eye-head coordination in the 4 tasks. We review significant differences in both the horizontal and vertical directions. This view shows the architecture of our model. We employed an EIH module to extract features from the eye-in-head gaze data. We employed a GIW module to extract features from the gaze-inward gaze data. We employed a head module to extract features from the head data. We applied 1D Ziyin and bidirectional GIU to extract features. We employed 2 fully connected layers to recognize user tasks. We evaluate the performance of our model on our dataset. We use both a cross-user setting and a cross-scene settings. We reported the results of using a window and using majority voting. We find that our model outperforms other methods in both cross-user and cross-scene settings. We also evaluated our model in real-world situations. We find that our model outperforms other methods on a real-world dataset. We identify several limitations of our work. First, we only explored the 4 tasks that are mostly commonly used in VR applications. Second, we employed non-interactive VR videos instead of interactive 3D virtual environments as our stimuli. Finally, we mainly focused on the differences between different tasks rather than the differences between different stimuli. In the future work, we plan to overcome the limitations. We want to explore the effectiveness of other factors such as human body movements and hand movements in recognizing user tasks. We want to apply our model to other systems such as driver system, AR system, and MR system. We plan to recognize other mental states in immersive VR, such as user cognitive loads and the levels of VR cyber signals from human eye and head movements. This is the end of my presentation. Thank you for your attention.
All right, thank you very much. And actually, I think I forgot to read the title of this last paper, which is EHTask, Recognizing User Tasks from Eye and Head Movements, Immersive Virtual Reality. I'm sorry about that. Okay, so the now that all the 5 presentations finished, we are now, let's move on to the Q&A session. So actually we have many questions. So to be fair, I'd like to give you one question and then go around, and then if you have time, we'll do the second round and third round. Is that okay? So the first question to the first talk will be, maybe I can pick up not mine, from Riku Otono. So thank you for a nice talk. Do you think other types of bullet comments, such as colored or flickering comments, would make difference on the result? Do you have any words?
Yes, I think from my perspective, colors can play an important role on affecting users' perceptions. Imagine if bullet comments were colorful and in large scale, they might be distracting instead of being helpful for users understanding the video content. And in such case, the spherical static method should be more preferred by users because this method might be less annoying. Flickering problem might appear in the bullet comments moving methods. And static methods should encounter less flickering problems. Thank you.
All right, thank you very much. That's great work. Okay, so the next question to the second talk I want to pick up is from Pablo Figueroa. Thanks, Thuong, for your presentation. Why do you have 2D videos of the virtual environment inside the immersive experience? Why not having animations in the virtual environment and show users things in the same space as the tasks are happening?
Thank you, Yoshi, and thanks, Pablo, for the questions. So I think most of all was it's sort of a simpler sort of rendering for us to have that video, and then we sort of replicate that. And then another thing was basically because the working area within the space is directly onto the different parts. So I think what the video was showing before was actually one of the filters. So that's an oil filter. They actually have to remove the cap and change. So we didn't want to sort of render anything directly onto the environment. So that's exactly, they had a clear and almost immediate and similar simulations as in VR and translate directly into the environment straight away. So we don't want to sort of add anything on top of that. And it's sort of on reflection, our design process, we actually build a prototype iteratively, and we actually invite our industry partners to sort of going almost weekly or sometimes fortnightly to actually see the environments. And their comment, I think their comments will want to go with a video format because that's more common, more like sort of immediately translations of what they use for PowerPoint directly into the environment. So they exactly decided on a floating window rather than sort of rendered directly onto the environment.
Okay, thank you. All right, so the one question to the third speaker is from Stephen Feiner. What happens if there is a dynamic object that attracts the user's attention and which mimics the gaze trajectory needed to trigger a menu entry?
Okay, thank you for your question. Yeah, one of the design goals of the GazeDock is just to present the false triggering caused by natural gaze movement. And in our study one, we have examined the user's gaze movement pattern in natural gaze behaviors, but this natural gaze behavior was limited to typical VR task, and we tested 4 different kinds of VR applications. But if we intentionally design some dynamic objects to attract the user's gaze to gaze behavior to cause some intentional trajectories that may cause false triggering for GazeDock, as we have showed in our simulation that although we have fine-tuned our parameters, the false triggering rate could not be reduced to 0, but at a very low rate. And actually, we did not mention in the talk during to time limit is that for the triggering and for the triggering detection algorithm, we have also incorporated some minor parameters that for example, the users have to keep their gaze at a specific angle and if they, for example, leave the menu unintentionally and they quickly return to the menu, the GazeDock would not fade out immediately to further prevent the false triggering rate. And I guess that would be a very interesting topic to further explore in the future. Thank you. Yeah.
All right, thank you very much. Okay, so one question to the fourth speaker is again from Stephen Feiner. In OctoPocus in VR, could the crib sheet just be used as a 2D menu?
Thank you, Steve. And to answer your question, so in fact, the crib sheet is actually, I believe, from the original authors. It's inspired by the 2D menu as well. But in our case, the comparison is for gesture-based triggering, right? So I guess that the inspiration is from 2D menu. Yeah, that's to answer your question. Mm-hmm. So to apply it back, maybe that's an interesting application as well.
All right. Okay. Thank you very much. So one question to the fifth speaker is from Brandon David Zhang. Thanks for the great talk, as always. Could you elaborate more on the event detection for comparing saccade metrics behavior across tasks? I see the average was 600 milliseconds or more for the saccade duration in some tasks, and this seems quite large compared to expectation in literature. Perhaps this is due to using gaze in world data, i.e. Head movements are included in the analysis of gaze position.
Thanks for the question. In fact, we use the saccade duration. Well, it depends on the fixation detection method you use. If you use different methods, you will have different fixations and saccades. We use the in-head movement data for calculating the fixations, so that may be a little different from the traditional results from 2D images or videos, because head movements are not considered in that work. But the average of more than 600 milliseconds are sometimes common in similar works, so that is not very quite strange. Yeah.
Okay, thank you. Okay, so we still have time, so let's go move on to the second round. So the second question to the first speaker is from Huiyu Lu from Virginia Tech. Great talk. I was wondering, what is your thoughts of having potentially 3D view comments in immersive videos experiences?
Chair, can you repeat the question again?
I was wondering, what is your thoughts of having potentially 3D view comments in immersive videos experiences? Not to.
Yes. Bullet comments can enhance the user's immersive explorations, and I think that could be useful for education, advertisement, and entertainment, etc. And another great application for the bullet comment technology, I think it can be used in the asynchronized collaboration, because it can easily support a large scale of people communicating, and that would be great for the collaborative tasks in immersive environment. Yeah, thank you.
Okay, thank you. All right, so the second question to the second talk is from Bruce Thomas. Have you thought about passive haptic props?
Thank you, Kiyoshi and Bruce, for the questions. So the use case scenario for our industry partner is that they are interested in posting our physical VR headsets to remote location where their clients deploy these hydraulic machines so that they can train maintenance workers on site who have direct access to the machines, who normally deploy in the very remote areas of Australia. So that's why we need to stick to like Quest 1 and 2, and sometimes we have offline online mode. The multi-user scenarios was for us to use for design, but when we posted out, we had to turn that off so people can actually use it completely offline. And that's why we were limited in terms of our sort of other tracking of physical props, because we won't be able to be on site to actually install or sort of configure those. We can only post our Quest headset as they are, get them to charge and give them instruction on how to turn on the app. But interestingly, all of our participants comment on the fact that, you know, it will be great to have haptic feedback because especially during traditional training as well, our trainer brought our physical props because one of the physical prop is a very heavy, it's all sort of like steel caps cover on the filter, which is extremely heavy to lift and need to be sort of very handled with care. So a lot of the participants mentioned that this is a complete different from sort of holding a VR Quest controller and sort of turning the bolts and all that stuff compared to actually doing that on the physical machines afterwards. So it's still an open challenge for us. We actually, you know, we're not sure how to sort of particularly solve that, but we're discussing with the industry partner, and they're quite okay with, you know, clearly indicating that there will be differences in what you feel in VR, which is almost nothing, compared to what you actually have to do on a physical machine. Thanks.
Okay, thank you very much. So the second question to the third speaker is from Riku Otono. While showing a peripheral menu, user's field of view is limited, right? If so, how does this limited field of view impact on your user experience?
Yeah, thank you for your question. Yeah, the appearance of the menu is actually a very important factor that we considered in designing the GazeDock to minimize the impact of limiting the FOV of the users. We have designed the GazeDock to be semi-parent, and we also introduced fading and fade out animations to minimize the distraction of the user's attention, and also as we have mentioned in this paper, you can refer to any manual interaction cannot totally avoid the occlusion of the content of the background context, especially in VR, where immersiveness is very important. And actually, the design of a peripheral menu is one of the, as we believed, one of the preferred methods to minimize the content occlusion. And if we calculate the percentage of the contents that was occluded, the peripheral menu could also reach a very low rate. And as existing works have shown that when we occlude the peripheral of the user's FOV and leave the central of the FOV unoccluded, the users will feel more comfortable and more at ease when during usage. And I believe this could answer your question. And also, as you suggested, further improving the GazeDock is also in this direction is also worthwhile. And for example, if we can further reduce the size of the menu and use some gestures to support the interaction, may be more preferred by the user. And thank you for a suggestion. We could consider this in future. Thank you. Yeah.
All right, thank you very much. Okay, so the second question to the fourth speaker is actually I will pick mine. With regard to OctoPocus, can you support those gestures that are similar in trajectory to each other but different in speed, acceleration?
So thanks, Kiyoshi, for the question. If I could double check, your question is about, say there are two commands to trigger, and could a slower one trigger A and a faster one trigger B, correct? So the challenge here would be, it means this would affect how fast the command selection is. So in our case, the OctoPocus implementation, when the user slows down, this signals us that they are having difficulties. This is as similar to the original OctoPocus as well. So we set a threshold of 250 milliseconds. If they do not move at all, we will then trigger the guide automatically. So in this case, a slower speed would suggest a novice user. So that's why this could be challenging if we implement different speed for different gesture. So a suggestion for future work could be perhaps exploring how the gesture itself could the mapping be improved between gesture 1 with command 1, right? How can we make it more familiar to the user or easily executed? Yes. So thank you for the question.
Thank you very much. Okay, the second question to the last talk is from again Riku Otono. Great talk. How long the model take to recognize user task? Is it possible to recognize user task in real time?
Yes, of course. As you can see from our model is very lightweighted, and the running time for it is only a few milliseconds, so it can actually be used to for real-time usage. Thanks for the question.
Okay, thank you very much. So we have 5 minutes left. So let's do the third round very quickly. So please make your answer short. Okay, the third question to the first speaker is from me. In 360 video, you will miss many comments around you. Do you think it's okay? Or do you want to add some mechanism to guide the user gaze to like a popular comments on your back?
Dear Chuck, can you repeat the question again?
Should I repeat my question?
Yeah.
Oh, okay. You know, it's 360 video, so the comments will be around you, every direction. Yeah. So so sometimes you will miss some of those comments. Do you think it's okay, or do you want to add some gaze guiding mechanism?
If you want to recognize where the comments were yours and where are the others comments, you can change the bullet comments of yours into other colors for recognition. The gaze that this might be useful, but I think that should be further studied for the further application of the gaze technology in the bullet comments technology. Yeah.
Thank you. Okay, so let's move on. The third question to the second speaker is from Pablo, second part. I see your purpose, but that could complicate understanding because the user has to do the mapping between the tasks in the space of the 2D screen and the 3D space where they are. Any thoughts?
Thanks, Kiyoshi, and thanks, Pablo, for the follow-up question. So yes, indeed, there needs to be a certain mapping between what they've seen in the 2D task float and then the video screens on the screens there. But essentially, I think during our discussion with a trainer in the industry partner, because they actually had a training manager that we work with, this is actually one of the tasks that the maintenance worker had to do as well. Because in figure 3 of our paper, we sort of show a snippet of what they normally receive as paper training, which is a localized photos of where what the parts should look like, what tasks, a textual description of what tasks that need to be done. Comparing the size of the HPU, you actually have to go walk inside the HPU, locate where the parts are. And I think with our sort of training system, having a 2D system for them to translate into 3D parts is part of the training that we work with the industry partner to work on.
Okay, thank you. So the third question to the third speaker is again from Stephen Feiner. In a multi-person environment, could that be your means of attack if someone else causes an item to attract your attention that way?
Yeah, just to answer that very quickly. Yeah, yes. We have not considered intentional attack in designing our algorithm, and actually also in many of similar techniques, we did not they did not consider attack. But this is a very common topic in the usable security research area, and we are also planning some future work in this direction, and if you're interested, we could contact later. Yeah.
Okay, thank you. So the third question to the fourth speaker, maybe I can extend the last question. So by incorporating the speed and acceleration, maybe you can also, practice calligraphy in 3D space, or maybe you can come up, some 3D gesture that has some, the nice rhythm or something. Not only the tragic geometry, but also the time parameter can be incorporated. What do you think about it?
Could you elaborate a little bit more about the time component, Kiyoshi?
Yeah. So maybe you can start slowly and then they accelerate in the middle and then slow down at the end, or maybe vice versa. That you can change the speed in the same trajectory, and then maybe you can have a variations. So that do you think you can support that kind of gesture too?
I think our current implementation do not support that currently, but I'll be interested to see how that could affect our results. Yeah, would user find it difficult to adjust their speed of execution? Yeah, so yeah, I would like to see if how the results would look like as well.
Okay, thank you.
Good suggestion. Thank you.
Thank you. And the third question to the last speaker is from me. How much do you think you can scale up the number of classes to recognize?
Well, in fact, it depends on how to define the tests, because some tests are easy to recognize and sometimes they're very similar and hard to recognize. I have to say is that in Peripherals, people usually recognize from 2 to 7 tests, and I don't say more tests. Yeah, that may be the range for current research. Yeah, thanks for the question.
All right, thank you very much. So can you turn on your cameras, all the presenters? Okay, so this concludes the session of 3D UI. Thank you very much.
Thank you, Kiyoshi. Thanks,
Thank
everyone.
you. See you, everyone. Bye.
See you.